What I'm going to talk about today is I'm going to start with this filtering stuff, which is, of course, as you know, is sort of different than the kind of filtering that I talked about yesterday. So it's got the same word in it, but this is more probably better characterized as signal extraction. So it's going to be trying to track something that is evolving through time when you observe it with air, if you will. So we'll look at some examples of that. Stochastic volatility model is one. So you want to track the variance of something over time, or the local mean in the context of what we were talking about yesterday. So we'll talk about some linear models. So that's this sort of Kalman filter. We'll talk about some nonlinear models for, and I'll use stochastic volatility as the example here. And one way to do this sort of signal extraction in these models is, well, to use some analytic formula, which are simple to use in a linear model because everything's Gaussian and they're just linear regressions, right? So we'll use linear regressions there, and that's sort of simple. But in the nonlinear thing, the regressions are nonlinear, and so figuring out what the regression function is difficult. And then it turns out that there are some, pretty simple simulation methods that you can use and that often work. So I'll talk about those, and those are examples of Markov chain simulation methods, or Markov Chain Monte Carlo methods. So that'll be the first lecture today, and then the second lecture will be talking about estimation of parameters in these kinds of models, where you've got a break in a coefficient or something, and you might want to estimate the break date and do inference about it, or you might have some martingale variation in some component, maybe a parameter, and you want to estimate that variation or the other parameters of the model. So that will be the after coffee talk, and then Jim will come back after lunch, and he's going to do structural vector autoregressions, a tool used by macroeconomists a lot, and talk about what we've learned about those in the last 10 years or so, and then DSGE modeling. I look forward to seeing what he has to say about that. Okay, so let's get going. So this is the outline of this morning's lecture. So I'll start with some sort of general stuff. What's a general what's a sort of the canonical model I'm going to be talking about, and it'll could look like a macro model if interpreted right, and then I'll talk about some things that you might want to do with it, objects you might want to estimate or calculate, right, and then we'll spend the rest of the time figuring out how you might calculate those things, right. So first I'll work out some general formula, then go through some special cases, and then, as I say, talk about this simulation method, and then talk about how you might estimate or approximate the value of the likelihood, which is important, perhaps if you're doing maximum likelihood estimation. So here's here's sort of a general way to write down the model that we're going to be interested in. So it's I guess a buzzword. So it's in general nonlinear. It's got shocks and variables in it that are non-Gaussian. But it's got this sort of pretty simple structure to it. So you've got some observed variables y, and those depend on some states that are latent, s, and some noises, epsilon. So both s and epsilon you don't observe. What you observe is y, and s evolves according to this first order process, right, where s depends on where it was last period, and then there's some shock eta, and I'm going to think about both epsilon and eta as IID, I think, in everything I do. Is that right? I think that's right, in everything I do. You guys don't know that, but I can play my lecture forward and see that, in fact, I think, in everything I do, that they're IID. Right, so, here's a reference, and here's a reference, and these are different. This guy's so this is a statistician signal extractor, right? And then these guys are econometricians thinking about this as an economic model, and it's the same model, right? And it's just a question, what are you going to use it for, right? So let's just go. Okay, so the standard example of this might be a linear model, right? So this is just a linear Gaussian model, a linear state space model, a Kalman filter model, if you will, right? That's the way we'll sort of solve this. So the observables are linear functions of the state. The state evolves as a linear process right here, a VAR1, right? And the shocks are uncorrelated with one another in Gaussian. Okay, so that'll be, sort of keep this one in mind. We'll think about this. Okay, and other examples, might be, a Hamilton regime switching model, right, in which S, this state is now discrete at 0 or 1, and it evolves as a first order Markov process, right? So with a little fiddling, you can write it in the same way. That's all this does, where eta has to be a uniform random variable here, as it turns out. And, you could also think about, here's a nonlinear model, if you will, a stochastic volatility model. So think about my observable is, think about epsilon as like IID standard normal. So this guy has variance 1, but it gets multiplied by, if you will, a time-varying standard deviation. E to the st would be the time t standard deviation of y, right? And the log of this standard deviation, so e to the st is the standard deviation, the log of that is s, right? And this s might follow an AR1 or something like that, right? So this is a, time-varying volatility, I'll say Garchi kind of thing, even though it's not Garchi, right? I mean, it's the same kind of idea, okay? And so these are just kind of examples, and we'll do a couple of these in detail. So we'll do this one in detail because it's really easy, and we'll do this one in detail because it's fun, and highlight some things that are kind of useful to talk about, I think. Okay, so what might you want to do if you've got one of these models? There's some objects, some things you might want to calculate. So, let's let capital Y and capital S denote, histories up until the time of the subscript. And then, some things you might want to do is you might want to predict, right? So you might want to figure out what the state, some guess of what the state's going to be tomorrow, given the observables today, right? So this is the predictive density of S given Y. You might want to, of course, predict the observable, right? So what do I know about Y tomorrow, given the history of the observables today? So this is the predictive density for Y. It turns out, also, of course, by factoring the joint density of all of the Y's, you can write it as a product, right, in the usual way. So this predictive density multiplied together gives you the joint density, plug in the data, of course, that's the likelihood, right? So if you stuck in observables here, you stuck in data here, this would be the teeth component of the likelihood, or if you took logs, the teeth component of the log likelihood. So this is going to be kind of a key object, right, if you want to do estimation or something, right? And then sort of standard things that one might want to compute is you might want to do tracking, right? So you might want to figure out what the state is today, given your observables today. So this is the, in the jargon, this is the filtering problem, right? And the smoothing problem is, you've got a bunch of data on y in the past, y in the future, right? And you want to know what the state was in a particular day given data in the past, present, and future, right? So that's the smoothing problem, if you will. Okay? So we're going to talk about, general formulas for computing these guys given the structure, the formulas. Because of the structure of this problem, the formulas are kind of simple, have some structure to them. So I want to show you what that structure is, and then we'll talk about using that structure to do these calculations. Okay, so that's the thing. Okay, so sort of general formula, and I wrote down these are in Kitagawa, and they probably are. And I should have gone back and read this paper, but it's of course, right? You never have to read papers if you just think, right? So that's what I tried to do here. So let's see, did I think right? But I'm sure that these are, positive, that something like them is in a paper by a guy whose name probably spelled something like this. Okay, so here's the model, right? So y depends on s and epsilon. These epsilons and these etas, these guys are going to be IID, so we'll use that. S depends only on lagged s, okay, and this eta. Okay, right, here's prediction, right? So I want to know what's the density of little s, right, given past values of y, right? And, and so you can use a little trick here, right? Augment this with lagged values of s, right? And then integrate over, write this marginal, if you will, as a joint, right? And then integrate over the second argument, right? And then it turns out that, and then you take this joint, right? And you write it as this conditional times this marginal, in both cases, of course, conditionally on lagged y's, right? And then the key kind of thing here is to say, well, gee, if I know lagged s, lagged y doesn't help me at all, right? So I can get rid of that component. So, the way I think about my predictive density for s given lagged y's is just this filtered thing. What's my best guess of s at time t minus 1 given t minus 1? That's the filtering problem, right? And then I update that to get my predictive density of s, right? So that's a little trick, right, that you'll recognize this if you think through, most of you at some point went through these little Kalman filter things, right? And this is just an example of that, right? And of course, obviously to get the predictive density of y given s, little y given y, conditional on s and unconditioned, right? And once you've got this, right, this density is really easy because, given s, right, y is pretty simple, right? It's just depends on epsilon, right? So this is pretty simple given that. Okay, filtering, similarly, apparently it looks like I've used Bayes' rule here. So how did I use Bayes' rule? Blah, blah. Okay, yeah, look, right? So I want s given big Y, but big Y is just little y at day t and big Y at day t minus 1, right? And so now use Bayes' rule on this part, right? So that means I can take y and stick it over here, take s and stick it over here. That's what Bayes' rule is, right? Interchanges those. That's what I do here, right? And then, of course, you got to do that, right? You got to put that factor in, right? And then, and then you notice something cool here, right? I've got s over here and little y given s and big Y doesn't matter, again, because of the structure of the problem. So that just sort of, simplifies. That just sort of simplifies to this. So this is pretty easy to compute often. This is this prediction problem that we talked about, right? And this is the prediction problem that we talked about. So we got that, that's pretty easy, right? So that we can solve the filtering problem. In principle, anyway, the formulas look kind of nice. Smoothing turns out to be similar Actually, I don't think this formula is in this Kitagawa thing, but it's the same. It's a similar kind of trick. And, what do? I want now, what's my best guess of S at date little t given Y at date capital T, right? And what do? Well, you throw in this ST plus 1 thing, right? And then, and then you do some rearranging. And you can just work through this. Right? So blah, 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 right? And you get all the same things. But what's cool about this, or what's nice about this, right, is this smooth thing that you want, right? It's this filtered thing. So the only difference between this and this is there's a little t here and a big T here, right? And then times what? Well, times, the density of ST plus 1 conditional on ST. That's easy to compute. Right? Times, this factor, what's this? This is the smoothed estimate of S at date little t plus 1, right? Times the predictive density at S at date little t plus 1. So the way you work through this, and again, this is familiar for those of you that have gone through this Kalman filtering stuff, right? You do the filtering up to the last period, and then you work backwards to get the smoothing, right? So this is this working backwards things, right? So I go all the way forward, and then to figure out what my smooth value is at S at date t, I use information on what my smooth value is at S at date t plus 1, right? And you work backwards, okay? So those are these general formulas, okay? And they're kind of pretty, I think. I thought they were pretty. But of course, in any particular application, to apply them, you need to know what all these F's, you have to figure out what all these F's and stuff is. So that's kind of the hard part, right? So we've simplified things a lot, but not enough that for any particular model, you can just do it, right? You now have to sort of still dive in and get kind of dirty, greasy, if it was like you were working on a car or something. So, except no one works on cars anymore, right? Because you can't work on your car anymore. I can put oil in mine. I tried putting in windshield wiper fluid, and I put it in the coolant. Then I looked on the web to see what damage I'd done, and there's like 1 million people who have done this, right? Anyway. Then you take your car and you get it flushed. Anyway. So let's get back to work. Okay. So, So here's some special cases. So here's the simplest special case, right? So the simplest special case is the linear Gaussian model, right? And that's going to give us the Kalman filter, right? So let me just remind you, how you do that. And this reminder is useful. Well, if you know this, then it's not useful because you know it, right? If you don't know it, it's useful because it means that you could always derive it in like a minute, right? If you were like stuck on a desert island. And so here's the way you proceed. Okay, so here's the model. It's linear. And then, you just everyone knows this formula, right? This is your first econometrics class, right? If you've got A and B are joint normal, right, with mean, right, and covariance matrix, right? Right, if you've got joint normality, right, marginals are normal, conditionals are normal, right? Normals are nice, right? So in particular, the conditional distribution or density of A given B is also normal with this mean and this variance, right? Where the mean of A conditional on B turns out to be the original mean of A updated by, the deviation of B from its mean, right, times this linear regression coefficient, okay? And the conditional variance is this. It's the original variance minus what you learned about, right, A from B, which is just sigma AB, sigma BB inverse, sigma BA. Okay? Okay. So that's great. So this is the Kalman filter, and this is the Kalman smoother. right? That's it. All you have to do is interpret A and B correctly, right? And you're done, okay? So let me just show you that interpretation. So here's the model again at the top. Okay, so y is a linear function of s. S depends on lagged s. These epsilons are normal. Okay, the notation is standard. S little t slash k is going to be the mean of st given y through time period k. Pt slash little t is going to be that conditional variance. Mu t minus 1, that's the mean of y given lagged y. So this would be the best forecast of y at date t given lagged y's if you were using minimum mean square error. Forecasting, right, and sigma t minus 1 is that conditional variance. Okay, so so what's the common filter? The common filter starts, it says, suppose I know the conditional density of st minus 1 given y up through time t minus 1, and I know it's normal. Okay, so let's start here with some normality, right? And then, right, then you can see, right, because everything is linear here, these epsilons and etas are normal, right, that the conditional density of s and little y given lagged values of y is going to be normal. Okay, and we'll figure out what these moments are in just a second. Right, that's straightforward. Okay, now what's the filtering problem? The filtering problem is I want the expected value of this guy given, well, not y at date t minus 1, but y at date t, right? So all I have to do is take this guy and stick it over here, right? And then we're done. Well, if I call this A and this B, right, I'm just figuring out the distribution of A given B, right? So that's why this slide that I just had is the solution to this, okay? So all we have to do is figure out what these guys are, right? What the means are and what the variances are, and then apply, you know, Econometrics Stat 101 formula for the multivariate normal. Okay, so that's what this slide does, right? And it's just, you just look. So now you just look, right? And you're done, right? Well, you know, what's the mean of s at date t given t minus 1? Well, you know, heck, everything's linear here, so it's got to be f times my best guess of that, which was this, plus my best guess of that, which is 0, right? What's the variance of that? Well, it's the variance of that plus the variance of that, and these guys are uncorrelated, so you get this, right? What's my best guess? What's the mean of y? Well, the mean of y is my best guess of this, and I guess I just figured that out up here, right? Plus the mean of that, which is 0. What's the variance of that? Well, again, two pieces. The variance of the sum is the sum of the variances because they're uncorrelated. So, boom, right? What's my, this is the regression coefficient, right? So this is whatever it was, sigma AB, sigma BB inverse, right, term. Here in the jargon, you know, economists would call this beta because it's a regression coefficient. For some reason, it's called K here, traditionally called a Kalman gain, right? And then that's just, right, the covariance times the inverse of the variance, right? And now these are these little two updating equations. This is mu of A given B is mu of A plus regression coefficient times B minus the mean of B. That's what that is, right? And then this is this little variance formula, right? I've written it in a bad way here. This is a bad way to write it. This is a standard way to write it. But it should be written as, you know, the variance of A minus the covariance between A and B, variance of B inverse, covariance between B and A, right? That's the general formula. And here I've written it in a sort of more traditional way in this literature. But that's all this is. Okay, so that's it. Right? So going back, and this is, and again, I like this because I never remember these things. This is all I remember. And I tell students when I teach, and Barbara will verify this, that this is all you need to know in life, basically. You should know a couple of more things. You should know where your office is. and how to get home, right, and this. And that's sort of basically it. Okay. Okay, and you could, I guess, work out the log likelihood, right? That's pretty simple. All the y, the density of y, conditional lagged y is normal, right? So all I need is the mean and variance, right? Because it's normal, right? So the mean is this, and the variance is this, and you stick it in the normal formula, and boom, right? You have the likelihood, I guess here, this is the log likelihood, so I've taken the logarithm of that. Okay. And you could also, in a similar way, derive these smooth guys, right? Best guess of S using all of the data and its variance, using, again, the conditional normal formula, interpreting things in the right way, right? And Jim does that in his textbook, and this is this old book by Anderson and Moore, and this must be a recent edition of it. It's sort of 1976 or something is the first edition. Okay, so now let's do something that is kind of more fun, right? And so this is an example of a stochastic volatility model, and let's see what happens if we sort of change things around so it's kind of nonlinear. So we got a nonlinear problem, okay? So now, okay. So now instead of, before I had observable is S plus noise, right? Now I've got observable is, well, this state thing times noise. Okay, so it's nonlinear, right? But it's a product, right? So, we kind of know how to make products linear. We take logs, right? And so, that's what, that's kind of the trick here, so to speak. And let's do that. It's good to take logs not of negative numbers, right? Because that's a problematic. And so it's nice to make these numbers positive, right? And we know how to take numbers that might be negative and make them positive. We square everything, right? And then you got positive numbers. So take this expression, square it, right? And then take logs, right? And then, now my interpretation of S is just the log of the standard deviation, right? So it's log volatility or something. And this 2 here, this is what was H before, right? 2 comes from the fact that I squared some stuff, okay? And so this looks like, this is great, right? This looks like the model we just solved, right? Except I've got H is equal to 2, and what I had F now is equal to 1, right? But it's the same model, right? So you could think about just going about your business. The only complication here is that now this epsilon, if I started out with E being normal, like a normal 0, 1, right? What's epsilon? Epsilon is the log of E squared, right? So this guy's going to be non-Gaussian. It's going to have a distribution which is the log of a chi-squared 1, right? So we're going to think about doing filtering in a linear model, right? But with error terms that, well, one particular error term which is non-Gaussian, right? And ask what happens here. Okay. So there are 3 ways to do this. One way is just to ignore it. Gaussian, non-Gaussian, I mean, who knows? I don't know. Just do it, right? So, and undoubtedly someone's done this, right? And this is like, who? Okay, Ruiz and Shepard. Okay, I thought so. I was going to say, okay. So this is just like a quasi-maximum, like QMLE or something, right? So you could think about doing it. Of course, as usual, right, if you solve the Gaussian problem, which is linear, right, and apply that to a non-Gaussian problem, you get best linear predictors, right? So if you just thought about the filtering problem here, that would give you your best linear estimates of these states, right? So that's all kind of fine and nice, okay? And if you had to estimate some parameters, you'd get quasi-maximum likelihood things. Okay, so that's one way. Another way is, I guess you could work out analytic expressions for everyone. For everyone, everything, right? Has anyone done that? Oh, sort of. Okay. So, and someone sort of done that or tried. Okay, and or you can use some numerical approximations, and I'll talk about numerical approximations because it will. This is an example, and we'll learn a little bit about a couple of strategies for numerically approximating some stuff. Okay. So let's go. So I'm gonna focus right here. Okay. So there are two tricks here that we're going to use. There are two. I think a trick and a simulation method. Okay. So here's the problem again. The problem is these epsilons are non-normal. We know something about them. We know they're log chi-squared 1 things. Okay. So, right, here's trick 1. We're going to approximate this log chi-squared 1 density by a mixture of normals, right? So here, I guess following Shepard, or actually these numbers come from a paper by Kim, Shepard, and Chib. We're going to approximate this epsilon as a mixture of 7 normals. Okay? So think about epsilon as being a draw from a normal with this mean and this standard deviation with probability blah, right? This a normal with this mean and this standard deviation with probability blah, 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 right? And we got 7 of those guys. Okay? So I could write epsilon t as then, draws from these normals, right, times an indicator, right, where this indicator tells me which of these guys I'm drawing from, right? And I guess the probability that QIT is equal to 1 is given by these PIs. Okay? So by drawing this mixture, right, I can approximate this log chi-square distribution. Anyway, here's 7. I'll show you the log chi-square density and the approximation. And again, this is stolen from their paper. And here it is. You can see, that they look the same. Right? They look the same. They look the same. Okay? What's funny, very funny about this paper, I'm sorry, this is a great, wonderful paper, and I encourage everyone to study it. But, so this is like guys with way too much time on their hands. Okay? So this is what they do. They come up with this approximation, and then they solve all this. And then they've got like 3 pages at the back of the paper where they say, if you want to refine this approximation, do this stuff, right? And I mean, heck, you really have to really buy into your original epsilons being normal 0, 1 to want to refine this. Anyway, but that was pretty funny. But okay, so that's fine. So that's the trick. Right? So the trick is to approximate this log chi-squared 1 thing by a mixture of normals, and here are the coefficients, are the normals and the mixtures. And I've done some of this with n being much smaller instead of 7 being a smaller number. I think I wrote 2, but maybe 3 or something. I don't know. Okay, so that's the trick. Okay, and now we need some simulation methods. Okay, so I want to talk about see, I always get here. It's 35 minutes into this, and I'm on slide 17 of like 34, right? So I'm starting to freak out here, right? And then I'll run out of time at the end because I won't finish. Okay, anyway, so what we're going to do is we're going to use some Markov Chain Monte Carlo methods. And what I'm going to use here is something called Gibbs. Now, for those of you that know it, then you know it, and that's it. For those of you that don't, this hopefully will be useful. Okay, so Markov Chain Monte Carlo. Let me explain first each of these MCs. Right? I'll explain the second one first, Monte Carlo. Right? So this is right. Here's the game. You start with you got some random variable A, right? And you want to know something about A, right? You want to know. A is distributed F, right? And you want to compute the expected value of some function of A, like its mean or its variance or some quantile or something, right? And you don't want to integrate, right? You don't want to integrate because that's a bother, right? Maybe you forgot how to do that, right? Or this F is so ugly that doing the integration is hard or something. Right? So one thing you might do is that if you've got a random number generator and if you're lucky enough to be able to get random draws from F, right, then it's pretty easy to think about how you might estimate an population average, right? You would compute a sample average, get a bunch of these draws, right, and use your sample average as an estimate of the object that you want, which is the population average, right? And as long as these these A's weren't too weird and this function wasn't too weird, right? You would be able to estimate this thing with sort of in some sense arbitrarily fine precision if you let the number of draws get really big. Okay, so that's just the sort of law of large numbers. So that's the Monte Carlo bit of this, okay? So now the Markov chain bit of this is the, what if you can't draw from f of a in an easy way? So you don't know what that density is. So you can't compute these IID draws from your random number generator, right? So now, what might you do? Well, the game here is to instead of taking sort of independent draws from F, what you're going to do is choose a sequence of A's where these A's are generated by a Markov chain. So this guy's correlated with this guy's correlated with this guy, etc. Right? And you're going to choose this Markov chain in just the right way so that these draws, so this Markov chain has an invariant distribution which turns out to be f of a, and these guys aren't too highly serially correlated, right? So that this sample average thing is still going to work well. Okay? So that's what this Markov chain stuff is. Okay? And so what we're going to do is I'm going to talk about that in the context of this example. Okay? So I'm sure that's kind of what this next slide says. Okay, so this next slide says I'm going to choose my I plus first draw of A is going to depend on my ith draw of A. So I'm going to draw from this conditional density, and I want to choose this conditional density in the right way, and that's going to be problem specific, I guess, so that its invariant distribution is what I want. And as I said, the draws can't be too dependent, like if I kept drawing the same thing over and over and over again, right? Then this would be not good, right? So I want enough independence in these draws that this sample average works well. And I guess, the amount of dependence is related, the precision of this will be related to the amount of dependence and how big I choose n, right? So if I've got these guys are pretty dependent, I might have to make n really big. Okay? Okay. So there's some theory and there's some references I'll give you, I hope, that talk about this in general. I'm going to talk about it in a particular context. Okay, so this is one way to do this. This is one way to do this. So remember what we have to do, right? We have to choose this way of drawing these A's, right? So that F's the invariant distribution, right? And we don't want these guys to be too highly serially correlated. Okay, so this is there's a bunch of ways to do this. I'm going to talk about Gibbs, right? Others you have heard of are like Metropolis Hastings, and I'm not going to talk about that. I'm going to talk about this because this works well for this example. Okay, or is a natural way to proceed in this example. So here's the game, the sort of Gibbs game. Okay, so the Gibbs game here is you take A. A's the thing that you want to draw from, or you want to draw A. Think about A as being a vector with two elements in it. Okay? Call them A1 and A2. And I know you're never supposed to use superscripts because people confuse them with powers. But I already have subscripts. So you have to put the index someplace, right? So I'm going to put it up here. So don't confuse these with powers. I'll do that tomorrow too, and I'll square them, right? So then you should be confused, okay? But that's okay. Confusion is a good thing because you have to, then it forces you to think, right? Okay, so here's what we're going to do now. So take A, suppose you can break it into two components, okay? And I want to get draws from this, okay? So here's the game, right? Well, write the joint density, right, as the product of the conditional of A2 given A1 times the marginal of A1. Okay? And then, right, well, now you can see how this is kind of going to work, or how it might work, right? Suppose I happen to draw A1 from its marginal, from the correct marginal, right? Well, then, right, if I drew A2 from the conditional distribution of A2 given that A1, I would have gotten a draw from the joint distribution. Okay, so that's kind of it, right? That's it. So stop, take a breath, sink in. So it's pretty obvious, right? So now what we're going to do is we're just going to iterate on that. Okay, so, here's my ith draw of A. Break it into two components, right? So now what I'm going to do is I'm just going to iterate on this thing, right? So now how do I turn this AI into AI plus 1? How do I get my next draw of these two random variables? Well, the way I get my draw of A1, right, is to draw from the conditional density of A1 given A2 and stick in my last guess of A2 here, right? And then how do I get my draw from A2? Well, I want to draw from the conditional density of A2 given A1, and I just drew an A1, right? So this allows me to move from that to that, right? And if these conditional densities are sort of nicely behaved, right, this Markov chain is gonna draws from this are gonna converge to draws from the joint distribution, and they're not going to be too dependent, and I can do this averaging. Okay, so I got to show you some. So I'm gonna the next slide is going to be. So this sort of like seems sensible. Shake your head. I told Barbara sitting in the front she has to shake her head regularly, so give me some positive feedback, or else I don't feel very good, right? Okay, so it's just this, right? Okay, now you kind of have to think, geez, when is this going to mess up, right? And so I want to show you, I want to talk about when it messes up, right? And then I want to talk about how you might check to see whether it messed up. Okay, because that's what, okay. So when is this going to mess up? This is a little different picture than you have. Okay, but it's got the right idea. Okay, so when's it going to mess up? Okay, so here is, so So this should be, this is A2 and this is A1. So you have a picture that looks sort of like this in front of you. Okay. Now, right, I want to get draws from this joint density of A1 and A2, right? And it's got this funny sort of bimodal shape, right? And how am I doing the draws? Well, you know, I choose some A2, right, like right here, right? And then I draw, this is kind of like a helicopter tour. Whenever I see one of these, I think of the helicopter tour paper of Harold and Chris. This is a different picture, but it still feels like a helicopter tour. Right, so what are we going to do? We're going to be an A2, we're going to be right here, right? And then we're going to draw from the conditional density of A1 given A2, right? And what's that given? That's given by the slice of this guy, right? So if I got this A2, I'm going to draw some A1, right? Well, you know, in this particular weird example, that's going to be essentially from this part of the density, right? And then given that A1, I'm going to draw A2 along this slice, right? And that's essentially going to be from this density, right? And if I, you know, you can see I kind of get stuck here, right? In this particular weird example, right? Most of my draws are going to be here. I really need to be able to go poof and get over here, right? So I need kind of enough mass here that I don't get stuck. Okay, so that's one thing that could go wrong. You could have a weird density in which, you know, you don't visit everywhere, right? So that's a problem, okay? Or, you know, even if you've got a density that in theory you visit everywhere, if the probability that I draw an A1 from here is very high given an A2, and the probability that I draw an A2 is from here is very high given that A1, even though in principle I can get here, I'm going to need a lot of draws. You know, n's going to have to be really, really, really big, right, to break out of this to get over here. And then the way I've written it here, once I get over here, I'm kind of stuck. Right, I got a bunch of draws here. It's going to take a long, long time to break out, right? So my n in this averaging stuff is going to have to be really enormous. Okay? Okay. So we kind of want to rule stuff like this out. Okay. The other thing is, you know, an extreme version of this is if you just have an absorbing point, right? So what if you get, you know, if you start with some A2, which happens to be some weird point, A2 tilde, right? And then if A2 is equal to A2 tilde with probability 1, I draw A1 tilde. And with that A1 tilde with probability 1, I draw that A2 tilde. I just get stuck. I just never move, right? So that's kind of think of that as a real extreme version of this, okay? Now, the reason I put this up is because I did this once, right? And so I'll show you. I didn't quite do this, but I sort of did this, right? And it's embarrassing. So, but I'll share that with you. Okay. So, you know, if you want to ask yourself, you know, does this stuff work? Well, I guess you need to know enough about the joint density to say, is it kind of one of the, do I have this problem or not, right? And, you know, sometimes if you knew enough about the density to know if you had this problem or not, you wouldn't be doing this. You'd just be drawing from the density, right? So it's kind of nice to have maybe some diagnostic checks, right, to see, right, do I have these problems or not, right? And what you might do here, it's kind of obvious what you might do here, right? What you might do is sort of do some of this Markov chain stuff, right, from different initial conditions, right? And then what would you conclude? Well, you'd conclude that if you kind of started down here, right, you were drawn from this guy, and if you started up here, you were drawn from this guy. So if you did these simulations from different initial conditions, right, you'd be getting different answers, right, and that would tell you, right, that something funny is going on, right? Or what you might do, I'll just go through this list, right? Okay, so that's what this is, multiple runs from different starting values, right? And you might, well, here, let me step back for a second, because I guess I thought through this when I wrote these slides up. So there must be a rationale here. Okay, so here's the estimator, right? So you're estimating this population average with the sample average, right? And if things are nice, you've got dependent but not too dependent draws, right, from the same distribution with the same expectation. So you're going to be able to think, in the usual way about this guy being an estimator of this guy, right? And it's going to be approximately normally distributed, right? With some variance that you could compute, right? This is the hack, right? Covariance, right, of this G. And we'll talk about ways that you might estimate that tomorrow. But, it's Newey West, right? It's Newey West or something, right? Okay? So you Newey West this guy, right? So then you could kind of compute, confidence intervals for this, right? And you could kind of ask, how big n has to be and stuff like that, okay? Then you could do this, right? Start this chain again from another place, right? And then you've got two independent estimates. You kind of know what their sampling distribution, you kind of know how far apart they should be probabilistically, right? You can do a difference in means test, right, to see whether they're the same, right? So this is a diagnostic that's used. Another diagnostic that's used is just, when you run this Markov chain, you run it like 1 million times, right? You could take the first 300,000 draws and the last 300,000 draws, leave out the middle 400,000 draws, right? And then you should kind of have independent things, right? And you can see, do those give you the same answer, right? So these are sort of standard diagnostic tools, right, that people use. I'm sorry? Should not. See, I got this wrong, right? Okay, should not. Thank you. Yeah.
Is there going to be any information in the Newey West itself, like the generated data?
Yeah. So you can learn how serially correlated these guys are by computing the serial correlation coefficient. Now, it's a little, yes, okay, but. Right, it might be kind of hard to see, right? So imagine this example, right? It might look like, all of these draws are they're kind of independent of one another, but in fact they're really dependent because they're all draws from this and not that, right? So, it's not necessarily looking at the AR1, AR2, AR5, AR10 coefficient, right? Right, in something like this, you'd have dependence, but it's really long-range dependence. Okay, so now what we're going to do is let's just crank through this example and see what you might do. Sort of armed with this tool now. So here's our model. X is this product thing. Log standard deviations are random walks. Square things take logs. You get that. Right, so this is all stuff we've seen before. This error term epsilon, we're going to write it as what? A sum of some indicators times Gaussians. Right? We know the mean and variance of all these Gaussians. Right? This epsilon the distribution of epsilon is a mixture of these, right? So these QITs are zeros and ones telling us on any particular date which of these normals I happen to draw from. Okay. Now, here's kind of okay, let me just go through this, blah, blah, blah. Okay, so let's do this. Let's solve the smoothing problem, I guess. So the smoothing problem, compute my best guess of the standard deviation, which is, well, what's the standard deviation? I guess it's the exponentiated s, right? So that's the g function I'm interested in, right? Given all of the data that I see. Okay? And, here's kind of the trick that we're going to do. Here's the trick that we're going to do. The A, the thing that I want to draw from, what do I care about? I care about S. Okay? That's what I care about because that's what I want, right? But I'm going to define A in a particular way so that drawing these conditionals, A1 given A2, A2 given A1 turns out to be really easy. Okay? So what I'm going to do is I'm going to take this is the thing I'm interested in. This is what I want to draw from. I want to draw from the density of this. But what I'm going to do is I'm going to add some other variables here that are going to be useful for making these draws. And the variables that are useful for making these draws are these Q's, these 0, 1 variables saying which normal I'm drawing from. Okay? Now, why is this simple? Why is this a good idea, right? Well, suppose I knew what these Q's were. Suppose at each date, right, I said, aha, at this date I'm taking a draw from a normal with mean 5 and variance 23. And another date, I'm drawing a normal from a mean 4 and variance 16, right? And I know those normals, and I know at which date I'm drawing from those normals, right? Well then, heck, right, what do I have? I just have a linear Gaussian model where I have heteroscedasticity. I have variances and means that change, but I know them, right? So all I do is, Kalman filter stuff, linear Gaussian stuff, where at each date I mess around with this formula a little bit, right? But it's still a linear Gaussian problem. So if I knew what these guys were, right, then I know these guys are going to be conditionally normal given the y's, right? And I know how to compute the mean and variance of that conditional normal distribution. That's just Kalman filtering, Kalman smoothing stuff. It's nice and linear. So drawing these guys is trivial, right? Because it's just running a Kalman filter, Kalman smoother, and taking draws, right? Okay, so that's why I'm going to augment this. Okay, so that must be what this next slide says, I bet. Yeah. If I know what these Q's are, I know these indicators of what normal I happen to draw from, drawing the S's is trivial, right? It's a linear model. So boom, I got it. Okay? So drawing A1 given A2, drawing the S's given the Q's is simple, right? So now I have to think about what's the other side of this. How do I draw the Q's given the S's, right? Because I got to go back and forth. Well, here's a form. Here, I got to rewind. Okay. Drawing the S's given the Q's is simple, I said. It's simple, okay? But you need to draw. Remember we did these calculations? I computed, when we did the Kalman filter thing, I computed things like what's the mean of S and what's the variance of S at date t given the y's, right? I have to get a draw from this big vector, right? So I need the entire joint distribution of all of these S's. That's going to be normal, but I need all those covariance things, right? What's the covariance between S at date 2 and S at date 50 given Y through time period 100? So I need all those covariance things too, right, to do these draws. And that turns out to be pretty simple to do, right? Here's a paper that tells you how to do that in a nice recursive way. Okay, this paper. Okay. The first time I did this, I didn't know about this paper, so I just did it. You could just do it too. You could just do it, right? If you're a macro guy dealing with 200 observations or something, these are just 200 by 200 matrices, so you just do it, right? If you were in another field where you had 2,000 observations, that would be harder, and then these little tricks are really important. Okay, so I know how to draw from these guys given these guys. I have to say, how do I draw from these guys given these guys? Okay, well, that's pretty easy too. That's actually really easy. Because if I know S, then I know epsilon, right? and epsilon's just a mixture of normals, right? So the probability that QIT is equal to 1 given S is just, just Bayes' rule, right? So this is just trivial Bayes' rule, right? So that's the probability that this is equal to 1. Given the S's, it's just this, so I just draw from this. This is just Bayes' rule, as simple as can be. So that's where I've got these normal densities here. Okay, so that's really simple. So putting this together, right, I can just do it. I'll show you some results from this in a couple minutes. Okay, so now, so I have 29 minutes left. I'm on slide 26 of 34. We're okay. So you don't want to go over, because that's bad. You also don't want to end at like 10:10, right? Because then you didn't prepare enough, right? And that's bad too. Okay. So here's some here from macroeconomics. Here's some versions of this, right, that you've seen. So Cogley and Sargent have a multivariate version of this, right, where they have stochastic volatility in the E's, kind of the sort that I've talked about. It's a vector sort of thing. And they put in some time-varying coefficients here, too. That's just icing on the cake, if you will. Again, that's sort of all linear, so easy. So this Cogley and Sargent, I forget which one. There's a couple of these things, right, doing this. There's this is kind of a reduced form VAR, as I remember. There's a structural VAR version of this, right, in a very nice paper by Giorgio Primaceri. There are versions of this where these E's and these phi's don't follow. Remember, I have stochastic volatility following this random walk process. I have log standard deviations following this random walk process. I think that's what these guys use and what Giorgio used, right? Sims and Jha have a paper in which they have Markov switching here, right, on these guys, so you get stochastic volatility that way, right? Same kind of stuff. Now this one in particular, the mechanics are going to be different, right? Because the stochastic process for the volatility and the phi's are different. So it's a different mechanics, right? But same kind of basic idea. Okay? And let me show you a version, some output, if you will, just because you need to see numbers every so often to wake up. Let me show you a version of, if you will, like a Cogley-Sargent thing, a reduced form VAR, okay, but a real easy one. So we're going to make Y a scalar. Okay, so it's just a simple autoregression. I think it's like an AR4 or 3 or something. Y is quarterly GDP growth rates, right? This comes from a macroannual paper that Jim and I wrote several years ago. And so we're just going to estimate this AR4 model where we've got stochastic volatility and we've got potential time variation in the phi's using basically this algorithm, right? And then we're going to, from, if you have an AR4, you could compute what's the standard deviation of this, right? Which would be year-over-year growth rates of GDP in this thing, right? So given phi's and given the variance of E, I could compute what's the standard deviation of year-over-year growth rates of GDP, right? And I just plug in my estimated phi's and my estimated sigma E, right, to do that, okay? And so, here's a picture. This was in 2002, right? You don't have this picture, I think, because I added it this morning because I thought I'd run out of time, so I needed to stretch it out, right? And so, right, so this is GDP, this solid line in the middle, this dashes are something, I think that's the data, absolute value of the data or something. And what do you see? Well, the absolute value of the data is highly volatile and then less volatile, right? And if you compute the standard deviation using this stochastic volatility thing, well, you get what we now recognize, right, is the volatility decline that occurred in the early 1980s. Interestingly here, right, or what was interesting to us is that even if you estimated this volatility in kind of this flexible way, right, it looked like the volatility was kind of a step function, right? So that was interesting, I thought, or we thought when we did it. Okay? Okay. 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 Now here's like a souped up version of this. So let's go through this one because I'm looking at my time here. Damn. Okay. Here's the souped up version of this. So So this looks like this. Think about this. This y in this example is going to be inflation. Okay, so here's the model. Inflation has a permanent component, that's tau. It's called a permanent component because it evolves as a random walk, right? So we'll think of it as a low frequency bit. Right, so inflation has a low frequency bit, and then it's got some white noise bit, right? So that's epsilon, right? So you could think about estimating this model and do the usual kind of calculation. Look at the first difference of inflation. The first difference of inflation is going to be the first difference of tau, which is eta. And the first difference of epsilon, which is a first difference of white noise. So this part on the right-hand side is going to be what? Well, if everything is white noise here, this guy's going to be correlated only at lag 1 and have some negative serial correlation at lag 1, but 0 every place else, right? So this guy is going to be, an MA1, right, with negative serial correlation, right? So this is the model for inflation, which is an integrated, that is, you have to difference it once, a moving average model. So an IMA11 model, a popular model for inflation, that people have used over the last 40 years or so. Okay, so what we were interested in this paper was to ask, well, so what if we take this basic model that people have used for a long time and ask, maybe over time, the relative importance of these components has changed, right? So maybe this variance, the permanent component used to be important. It had a big variance, right? But now it's small. And maybe this component used to be important, and now it's more or less important, right? So we wanted to take this model and do it where we allowed the standard deviations to evolve through time. Okay, so this is the usual version of this, right? You'd call an unobserved components model. You're breaking inflation into two components, a permanent component and a transitory component. So that's the unobserved components part. And now we're going to layer stochastic volatility on top of that. Each of those components, right, has some innovations that that follow this stochastic volatility thing. Okay, so here you go, right? So, it's the same thing, only there's just more stuff, right? So Y is composed of these two components. Tau is composed, so you're just going to do this. Right, so now you're going to do this, right? So now do this. So now take epsilon t. We want this guy to be a stochastic volatility thing. We know how to do that, right? So take epsilon t, square it, take its log, blah, 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 right? It's got to have a mixture of normals, right? Take eta, it's got stochastic volatility, square it, take its log, blah, 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 same thing. It's going to be a mixture of normals, right? same mixture coefficients, right, but different, these, when you draw these Q's, that's going to be at different time periods, right? Here's the stochastic volatility evolution, right? And now you could think about doing filtering or signal extraction here in the sort of same way, right? You just have to sort of put another layer on top of this. So now the game is this, right? So now take A and break it into 3 bits, A1, A2, and A3, right? What's A1? A1's going to be tau. That's this permanent component of inflation. Now, if I know these standard deviations and I know these Q's, again, this is just a linear Gaussian model, right? So I can draw the taus, right? Just using the usual formula. Okay, now what's the next step? We'll take this guy, stick it over here, bring another thing over here, right? Well, if I observe the taus, right, then I observe the first difference of the tau, that's eta, right? And I can do stochastic, we learned how to do that, right? How to get a draw from that. And I guess if I know the tau, I subtract it from y, I know epsilon, right? I do what we just did before there, right? No muss, no fuss, right? And now, well, now I got all of these, and then how do I draw these Q's? Well, the same way we did it before, right? So you could put another layer on this, right? It's kind of no big deal, right? You could add another layer on this, and another, 17 layers, get a whole bunch of different papers out, right? They would start looking pretty silly, but, what the heck, right? A paper's a paper, right? Okay, and that's what it's all about. Okay, so let me show you some results here because they're kind of fun. Okay, so this is based on 10,000 simulations. We're going to ask where I threw the first 1,000 away. You start this Markov chain someplace, right? So you worry the first set might be influenced by where you started, right? So there's always this case where you throw a bunch of them away. So I threw 1,000 of them away, right? And then here's inflation. You'll recognize this for the United States, right? And then here's this permanent component. Here's my estimate of tau that came from doing averaging. Now, what do you see? Well, it kind of does what you think here. It's smooth. So deviations of inflation from tau are these epsilons, right? So these epsilons seem to be pretty important here. Tau is not varying too much. It's pretty smooth. So its volatility is pretty low, right? Once you get back here, right, tau, right, and inflation are moving a lot together, right? So most of the movements of inflation are tau movements, permanent movements, not these epsilon movements. So it looks like these point estimates, right, are consistent with there being important volatility changes in this permanent component of inflation. I think that's what. Well, okay. I'll show you in a few minutes. I'll show you estimates of sigma eta. Okay. So now what I want to do is think about these. Here I did 10,000 draws of this thing. Is 10,000 enough? Right? Maybe I'm in one of these weird bimodal kinds of things or something, right? Maybe that's a problem, right? So here is estimates of tau, these smooth estimates of tau using 2 different independent sets of draws with different initial conditions, right? And they're both plotted here. And this is the difference in them, right? So that feels okay, right? You feel pretty happy when you see that. Okay. This is a little different, and you feel a little less happy about this. Okay, so this is so now sigma eta is the standard deviation of the change in the permanent inflation component, right? And here are the estimates of that. So you can see this is the 0 line right here. So you can see this volatility was, higher here, and then it came down a lot, right? And then it looks like it went up a little bit here at the end, right? But it's pretty low over this period, high over this period, right? And suppose you ran this thing again, right, with different initial conditions, different random things, right? What do you get? Well, now you can see a difference between these two, right? So it looks like, there's some simulation error, right? How big is the simulation error? Well, here are the differences. I mean, maybe you worry about this, maybe you don't. I didn't lose sleep over this. I lost sleep, but not over this. Okay, I'll tell you what I lost sleep over in just a few minutes. Okay, so what you might want to do is look at these draws, right, and see how much serial correlation there is in them. Now, each draw of tau is really a draw of this history of tau, right? So I've got taus for all dates, that's one draw. And then I got tau for all dates, that's another draw, right? So I could compute serial correlation in the taus for each date, right? And I think I've averaged them here, right? And, it turns out that they're not very serially correlated, right? So 10,000 draws with a process that isn't very serially correlated, I've computed this long-run covariance matrix, divided it by n, so this is like the standard deviation, right? So this is pretty small. It's about less than 1% of the average size of what this tau thing is, right? So that's why you couldn't see it, right, when I plotted them together, right? So that kind of feels good. This guy, this sigma eta, this is a harder thing to estimate, apparently, right, with these kinds of, it's more highly serially correlated, right? This Nui West thing is, well, it's smaller in absolute value, right? But this guy is also smaller than this guy on average, right? So you have about a 3% standard deviation, right? And that turns out to be about what you see here. That's like 3%, right? Okay. Now I want to tell you, here's a sin I committed once. I only committed it, well, usually you commit sins more than once, right? That's why you keep going to confession. But this sin, I think I only, no. Okay. I only knowingly committed it. I never knowingly committed it, okay? But I committed it twice. Okay, so here's the problem. Here's the problem here. Think about this model. Okay, see, I should have thought about this before I did it, right? I didn't think about it. What I had done is I had done this macro annual thing, standard stochastic volatility thing, and then then we needed this model, and I said, I can just use the same computer code, right, spruced up a little bit, and I'll just turn it on and then go hang out, right? And so this model was used in this paper with Jim Stock and also in a paper with these guys. I was going to call this paper had a mistake in it. So I was going to call this Cicchetti et al., but I figured I should put my name here, okay? And so here's the problem. Here's the problem with this analysis. Okay, so here's what could happen. Suppose you do this. Suppose, you're doing this Gibbs sampling draws, right? And suppose you do this once, right? And it just so happens you get a bunch of sigma etas that are really small, right? So they're really small, right? So then what's going to happen? Well, you're going to go run your Kalman filter, Kalman smoother thing, right? And you're going to say, sigma eta is really small, so this tau thing's not very important, right? Your Kalman filter, Kalman smoother thing's going to estimate the mean and variance of tau. It's going to say mean's really close to zero and its variance is really small, right? So then you can take a draw from that and you're going to get really small numbers, right? And then you're going to look at differences of those, and those are going to be etas, and those are going to be really small, right? And then you're going to ask, what's the variance of those really small numbers? And it's going to say, it's really small, right? And then you're going to draw these taus again, and they're going to be really small, right? And so you're going to run into this problem, right? And you're going to run into this problem. It's kind of that something problem that I showed before, right? You're stuck, right? So you've got high, and it's going to take a large number of draws to break out of that if you happen to be unlucky enough to get some of those draws. So in this paper, we applied this model to inflation for like the G7 countries, or a bunch of countries, I don't know, a bunch of countries, 7 of them, let's say. And it turned out for some of the countries, this estimated sigma eta was really close to 0, right? And why was it really close to 0? Well, it wasn't because the true sigma eta was close to 0. It's because this thing hadn't been run enough, right? Or, I let this thing get too close to 0 and then it just got stuck there, right? And so there was a working paper version of this, and then some person, oh man, I looked up the person's name today, then I forgot, Ling Hu. So it's really, so this is an important lesson. So I always put, code on my website so that people can do stuff, and sure enough, Ling Hu, at some hedge fund, this person named Ling Hu, who I should know, I probably met. Is Ling Hu here? Okay, downloaded these programs from my website and for some reason was running them, was using them to model something, right? Hedge fund related, I guess. And uncovered and sort of sent me an email wondering about something in the code, and then we corresponded, and sure enough, this problem sort of surfaced, and it never would have. I mean, it certainly wouldn't have immediately, unless he or she had been able to get this code and then try and figure out what we were doing here. So luckily that was done between the working paper and finished version of this, so that we could correct this before the finished version was published. So that so that's just it's good to always put your code up on your website with all of your data as soon as you possibly can, right? Because there are people out there that will try and replicate your stuff, and you really want that done early, right? Because having it done late means then you're stuck, right? You have to publish these embarrassing, whatever they call it, errata or something. Okay. So that's that. Okay, so the last thing I'm going to talk about now is it's just something that we'll talk briefly about tomorrow. Maybe Jim might talk about it today. I don't know. But so, computing these likelihoods. So we've talked about how you do filtering, how you do, in these nonlinear models, how you do smoothing, right? How you get estimates of these guys using all of the data, right? And that turns out to be pretty easy using these simulation things. If you want to compute the value of the likelihood, what you need is the predictive density of y's, so you need filtered versions of these guys, right? And then you got to do some other things. So what sometimes people use is they do something called particle filtering. And particle filtering means different things to different people, but the basic idea, just because there are lots of these things, and so I want to sort of tell you where this jargon comes from by thinking about a simple example. Okay, so I'm interested in the likelihood or the density of yt given lagged values of y. Okay, and what is that? Well, we worked that out, right? It's the density in this model of yt given s, which typically would have a simple form that you could kind of figure out, right? Because it's just that, right? Times the predictive density of s given yt minus 1. Okay. So doing this integration is sometimes hard because figuring out what this guy is hard in particular models. Okay? So a scheme that people use is something called particle filtering. And let me just tell you the basic idea so that you understand where the word comes from. Here's like the simplest one in the world you might do. This is a dumb one, but it makes the point. Okay? So this is what you do. You figure out ways to get draws from ST given lagged Ys. Right? So you figure out how to get draws from ST given lagged values of Ys. And let's say you get a bunch of draws, a gazillion of them, right? And then what could you do? Well, this is just right? You could just use this very naive estimator of this conditional density. These little S's, these little draws, right, are called particles, right? And so this is kind of a naive, if you will, particle filter here, where you're just approximating this probability distribution by if you will, by this thing here by 1 over n, if these are independent draws. Now, there are much smarter ways of doing that. The smarter ways of doing that, it seems, have to do often with the particulars of the model. And so if you ever want to do this, you don't want to do this. You want to go read papers by these guys or other guys. But this is where I'd probably start. This guy, I read a bunch of papers by this guy Neil Shepard, on this stuff when I was thinking about these lectures, and they're all really good. So it's worth reading anything that he's written on this. Okay, so I've managed, I think, to stretch this 75-minute lecture into 90, and so I don't feel guilty. I don't have to refund money to the NBER. So this is what we've done. We talked about this signal extraction problem, different models. We talked about general formula, special cases. This was the linear models and the stochastic volatility models. We then talked about ways of doing this filtering in these nonlinear models and some special cases, and learned about one MCMC method, this Gibbs thing in particular, and then at the end I just briefly touched on this particle filtering for likelihood evaluation. Okay, so let's take a half-hour break and then come back for the next lecture.